Hey guys, today you're going to be needing your notes package open to page 24. If you don't have a notes package, that's fine. Just make sure you follow along, and when it comes to the calculations, I highly recommend that you have a separate piece of paper out and you attempt the calculations along with me. That being said, you are also going to need your data booklet, and I will post a link on Google Classroom so that you can download a digital version of it as well. And you are going to need a scientific calculator. And there is a link on Google Classroom if you do not have a calculator. So today we're going to be learning about quantifying acid deposition and monitoring its effects. So if we were in class, we would be doing a lab to talk about titrations. Unfortunately, we are not, so hopefully I can find an online app that will help you understand what a titration actually is. But a titration is used in order to quantify. So quantifying, we talked about last class in terms of qualitative and quantitative. Qualitative and quantitative are two different things talking about numbers versus observations. So quantifying is really talking about adding numbers to your data so that it makes it more concrete. So in the sense of a titration, we're trying to quantify the amount of acid in a solution, or we're trying to find the concentration. So to do so, we add specific quantities of a substance, and we'll just call this substance A, that is known to react with substance B until endpoint is reached. So again, endpoint is the point at which you have neutralized your substance. Okay, so neutralization is talking about an acid and a base. So we are going to be using acid and bases, which is what this whole chapter is talking about. So we use a burette, which is this substance to the side, and in this picture as well. So this is a burette, and this is used because it's highly accurate, okay? We are also going to use a graduated cylinder and a pipette to increase precision. Again, you're at home, so you won't be actually using these, but hopefully I can find an app. So what happens during titration? So we have a known. So what a known means is we know the concentration. So known concentration. And it is added to the unknown. Again, this means unknown, and I'm just going to write this time concentration. So we're trying to find the concentration of this substance based on the fact that we know the concentration of this substance. So when we mix the two, a reaction is going to occur. So step 2 is when neutralization actually happens. Okay, so this is when no more of the unknown ions are able to react. A color change we will be watching for, or you will watch for, in order to determine whether or not neutralization has happened. We know as soon as that color has changed, endpoint has been reached and neutralization has happened. So if you look to the side here, we have three different colors. Okay, so this is at the start of the reaction, so we had a yellow solution. We started adding our unknown in this burette right here, and it turned green. So this is where your endpoint has been reached. Okay, and usually we will stop here. And then as soon as it starts turning blue, you have to stop, okay? Because that means that you have equal number of your acid versus your base, and it has been neutralized. And if you add more, then you're going to have more base, or you're going to have more of your unknown in your Erlenmeyer flask, so this beaker looking object. So ideas behind titration. So in order to perform a titration, okay, let's get my highlighter here, we need to have a standard solution. So in a standard solution, and you can watch this video, so if you download the digital version of this, you can watch the video and it talks about what a standard solution is. Again, just to make things simple, I am going to summarize it. So a standard solution is a solution that's my short version of solution, with a known concentration. Now there are two methods for creating a standard solution, and generally you won't be doing this for Science 30. It would be the teacher that's creating the standard solution. But what we would do is create a solid, or we would have a solid, not create a solid, and then we would add water. Okay, so we would calculate, knowing all of our calculations for chemistry, we would take our concentration or our mass of our solid, add it to water to create the perfect concentration. Number two, if you have a liquid originally, because some of our chemicals that we get come in a liquid form. So in order to create a standard solution from that liquid form, we have to, again, add water. Okay, essentially what we would be doing is we'd be diluting it to what we want it, or to the known concentration that we want. Now, why would we want to use standard solutions? Simply because it has a known concentration. We are then able to use that data to figure out an unknown concentration. So if you've taken Chem, I don't know if it's in Chem 20 or 30, but you would have calculated concentration as well. They did it a little bit different than I do teach it in Science 30. You can use either or to calculate your concentration, unknown concentration. It is totally up to you. I'm going to show you both. But for the first one, it's going to be a little challenging because it is a chem level question. If you do not understand this way, that is fine. I will show you the easier short version for Science 30. So titration of an acid and base. So here, Chem 20 way. So this is your Bronsted-Lowry. This you should know, reaction of an acid and a base. So here we have our hydronium ions, and here we have our hydroxide ions. So the hydronium ions are acting as hydroxide is acting as a base, and then we create water and water because this donates, this accepts, gives up a hydrogen to become H2O, gains a hydrogen to become H2O. So we know that this is a balanced reaction. So in this reaction, the number of moles, which is represented by our coefficient up here, of our acid is going to equal the number of moles of the base reacted because it's a 1-to-1 ratio. So N actually stands for moles. So this you would have learned in grade 10. So you learned the calculation for moles, and then if you took Chem 20, they would have taught it there. Science 20 as well. So C, if you go to your data booklet, you can actually find these calculations right in your data booklet. So on page 10 in your data booklet, so I'm going to make this bigger so you can see it. So we have our calculation right here. So C equals N over V. So if we cross over here, C actually equals molar concentration in moles per liter. V equals volume in liters. And then N, which is right at the top, is number of moles, MOL. So all this is in your data booklet. You don't have to memorize them. They are given for you. So in our bubble here, we're going to put concentration. And it is measured in moles per liter. Now our V was volume. So we're going to put in this bubble, volume. This one must be in liters. So if we look at this formula over here, moles per liter, liters and liters have to go together. Okay, so first problem. Again, this one is hard, so if you don't 100% get this, that is fine. Don't panic. Wait till the next one and I'll show you the easier way to do it. Most kids like that way. So the table given shows you data from the titration of 4 10 milliliter samples of a solution containing hydronium ions. Okay, so we have hydronium ions. So hydronium, if you remember from one of the previous lessons, is H3O+. Phenolphthalein is an indicator, so that's the substance we're using to determine whether or not endpoint has been reached. And then we have a 0.130 mole per liter of sodium hydroxide. So sodium hydroxide, oops, I didn't mean to cover that up, but hydroxide. So sodium hydroxide, anything with hydroxide is telling you that you have the OH minus 1, okay? And that is my standard solution. So I do know a bunch of numbers that are given here. So I'm going to underline them. We have 10 milliliters. It says 4. What that means is we've done this 4 times. It doesn't mean we have 40 milliliters. It means we've done this trial 4 times, which is why you see in this data table 4 times, okay, or 4 trials. Okay, so we're only going to use 10 milliliters. So we know milliliters is a representation of a volume. Now we need to determine if it is an acid or if it is the volume of the base. So 10 milliliter samples of a solution containing hydronium ions. So hydronium ions, again, were your acid, so this is your volume of your acid. Then it says we have using a 0.130 mole per liter. So moles per liter is a concentration of sodium hydroxide. So hydronium was your acid, hydroxide is your base. So this is going to be concentration of your base. So that's what's given in my data so far. So I'm going to list them. So my concentration of my base right now is 0.130 moles per liter. Then I also know, and I'm going to leave some space because I do know I have to calculate a volume for a base or find a volume of a base, but I do know my volume of my acid, which is 10.0 milliliters. Okay, now in my data table here, I have a bunch of numbers. Okay, so I have 13.44 and 1.22. So it says volumes of standard solution. If I read my question up here, my standard solution was the sodium hydroxide. So technically, this whole data table is my base, or how much base I added. Now, if I look at my endpoint colors, okay, so I have dark pink, light pink, light pink, light pink. One doesn't match the other. So I wonder which one doesn't match. Well, dark pink. So this means that when the person did the titration, they overshot. So overshot means that they added too much of your unknown. Okay, so we don't want to use the data that's going to make our results inaccurate. So we're actually going to cross this one off. Okay, now I need to use these 3. So how much volume or how many milliliters did I add if I had a final volume of this and an initial volume of this? So in these, you would subtract, okay, because it's always final minus initial. So this is where you get out your handy dandy calculator. Oops, sorry. So my calculator. So I'm going to take 25.35 minus 13.44 equals, so 11.91. So I need to put that in here. So 11.91. I'm going to make my point big so you can see it. Do the same thing for all of them, so subtract them all. So we have 37.33, subtract 25.35, and you get 11.98. So you're going to record that in your data table, 11.98. And my last one, we have 49.22, subtract 37.33. And we get 11.89. Okay, now I can't use all of these volumes, so I have to calculate an average. So an average, what you are going to be doing, in any average, you add them all together, and then you divide by the total number that you have. Okay, so we have 3 samples, so we're going to add 11.91 plus 11.98 plus 11.89 equals. So 35.78, so I'm going to record that down. Sorry, 35.78, sorry, 7. Now, since I have 3 samples, I need to divide this by 3. So divide by 3 equals, so my answer is 11.9, and we'll keep the 2, but the 6 tells the 2 to round up, so 11.93. So I get 11.93 milliliters. Oopsies. Let's make that a little bit better. Sorry, guys. 11.93. Okay. So this was the volume of your standard solution. So this has to be the volume of my base, which is 11.93 milliliters. Okay, that was a lot of work for just a small question. So it says calculate the concentration of hydronium ions. So hydronium ions was acting as your acid. So we are trying to find Ca, which is our question mark. Okay, there's all my data. Now I need to write my equation. So we had hydronium ions, which is H3O+, plus we had our hydroxide ions. If we're to write this equation, acids donate, bases accept. So if H3O+ loses one, it becomes H2O. If OH minus 1 gains one, it becomes H2O. So we have 4 hydrogens on this side, 4 on this side, 2 O's, 2 O's, balances out to a 0, plus and a minus 1, balances out to a 0. So it's all balanced, which means we have a 1-to-1 ratio. Okay, so Chem 20 way. We're maybe half done. So we know that we have some data here. These two go together, and these two go together. So we have a C and a V for a base. Using your calculation or using the formula from above, C equals N over V. If I have a C and I have a V, that means I can solve for an N. Okay? So I need to rearrange this formula to solve for N times V, so on, and you're left with N equals C times V. Okay, since we can't mix these two, we have to calculate our base first. So this is our base, so this top one here. So milliliters and liters, that does not work together. So before we actually do anything, we divide by 1,000 to get, and you can do this in your calculator, 0.01193 liters, because we have to work with liters. So N equals, so my concentration of technically my base, volume of my base. So concentration of my base was 0.130 moles per per liter times my volume of my base, which was 0.01193 liters. N base. So now I multiply the two together. Let me move this over here so that you can see 0.130 times 0.01193 equals. So I get 0.00155. So we're going to keep it at 0.0155, and we're going to record that down. 0.00155. Now, N is measured in moles. Okay, so this was the moles of my base. Since I have a 1-to-1 ratio, that means if I have 1 mole of base, I have 1 mole of acid. So now we can do acid. Now we can calculate the concentration of our acid. Okay, so C is our concentration. N, since we know it's a 1-to-1 ratio, our N is this. Oops, sorry. So Ca, that's a bad A, 0.00155 moles divided by, now, my volume of my acid. If I go back over here, I have milliliters. That can't work. Divide by 1,000, because there's 1,000 milliliters in a liter. So you get 0.0100 liters. So Ca equals. Now with your calculator, you can just hit divide 0.0100, enter. So my answer is 0.155. And moles per liter doesn't cancel out, so you just get moles per liter, and then you box in your answer. Woo! Okay. Chem 20 way, really hard. I don't like this way. A lot of students don't like this way. So I'm going to show you an easy way. So this is, I call the Bodner way. Again, you can choose to do it either way. It is totally up to you. So we have 25 milliliter sample. So I'm only going to do a couple of these, and then I will post the answers to the other ones so that you can try them before you do your assessment. So 25.0 milliliter sample of methanoic acid. So we know that this is a volume. We have methanoic acid, H. Okay, so we need to write a reaction. HCOOH plus was titrated with a standard solution of 0.250 moles of sodium hydroxide. So I know that moles per liter is a concentration of NaOH. So anytime you have NaOH, it's only the OH that's reacting, -1. Okay, so I have to use my Bronsted-Lowry theory of acid and bases. So this is where your data booklet comes into handy. So you need to turn it to page 11. So we had OH -1, which is way down here. And then we had HCOOH. So we got to find that on here. Oh, there it is. Okay, so we have one here, and we have one way down here. So this one's higher. The higher one always acts as the acid, which means this is my acid, this is my base. So acids donate, so it's going to get rid of an H. It's a neutral to begin with. So we get HCOO. And then if it's neutral and you got rid of a positive, so you spent $1, you become negative. Plus, now this is going to accept, so now you have two H's, and you're adding a positive, so your bank account was in the negative, and you're adding $1, so you become neutral, H2O. Okay, so it should be balanced. 1, 2, 3 H's, 1, 2, 3 H's, 3 O's, 1, 2, 3 O's, 1 C, 1 C. 1 negative, 1 negative, we're good. Which means we have a 1-to-1 ratio of acid to bases. So this is why the Bodmer way works, because you always have a 1-to-1 ratio for science 30. Okay, 17.5 mils of sodium hydroxide, so this is a volume. We know now that the hydroxide part is the base. So I'm going to put base, oops, that's a bad B. And then this means methanoic acid has to be our acid. Okay, so I'm going to list the numbers that and the variables that I have. So VA equals 25.00 milliliters. Leave some space because we want the CA and the VA to be together. Actually, let's just write it. Now we have VB. So we have VB way over here. So 17.5 milliliters. And then my CB, 0.250 moles per liter. So this is the one that we're trying to solve for. So in your guys' data booklet, if we scroll back up, okay, this formula right here, CIVI equals CFVF. So I kind of play with this a little bit to make it easier. So I change my I's to A's and my F's to B's. So much easier to work with. So I'm going to write that formula. CAVA equals CBVB. So then I can rearrange this and just solve for what I need to. The great thing about this one is you don't have to convert the milliliters. As long as you have milliliters and milliliters, it'll cancel out and it'll work just fine. So I'm trying to solve for CA. CA and VA are being multiplied. So in order to get CA by itself, you have to do the opposite, which is divide. So we need to divide by VA. That's a bad color, I'm sorry guys. So I'll just change it, divide by VA. What you do to one side, you always do to the other. Now VA is over here, cancel. Now you just rewrite your equation. CA equals VB, CB, sorry, they're being multiplied, it doesn't matter which way they go, over CA. You must make sure you put brackets here. Whoops. And now you just substitute in your numbers. VB was 17.5 milliliters times 0.250 moles per liter. Close your bracket. Divide by A, which was 25.00 milliliters. Now looking at your units, milliliters and milliliters cancels out and you're left with moles per liter, which makes sense because we have a concentration. So handy dandy calculator. 17, oops, sorry, we need to put a bracket, so I need to clear that. Bracket, 17.5 times 0.25, close my bracket. You can get rid of the 0 because you didn't, the calculator doesn't know any different. Divided by 25 equals, so we get 0.175, done. 0.175 moles per liter. So much easier than the last one. Okay, I'm going to do one more and then I will do the rest and post so that you can attempt them before you try your assessment. Calculate the volume. So it's saying you want the volume. So V, we don't know if it's A or B yet, is a question mark, of a 0.150 mole per liter solution. So I know that whatever the unknown is here, it's attached to this because they're together. So C of whatever this is equals 0.150 moles per liter containing hydrogen carbonate ions. Ooh, hydrogen carbonate ions. So let's see if I can find that. Hydrogen carbonate ions, hydrogen carbonate ions. I don't see that anywhere here. Okay, so data booklet is an amazing thing. So go to your periodic table. See if you can find hydrogen carbonate here. Right there. HCO3 minus 1. Okay, so I'm going to actually write that so that I have it. So we have HCO3 minus 1 plus is reacting with a hydronium ions. So hydronium ions, H3O plus. Again, that's why I said you should know your hydronium ions. Present in 75.5 milliliter. Okay, so we have 75.5 milliliters. That's a volume of 0.200 moles per liter. So this is a concentration. 0.200 moles per liter. Okay, so of a hydrobromic acid solution. So we know we have hydronium ions in this acid. It's pretty self-explanatory that H3O plus is the acid and the HCO3 is acting as the base. But we can double check. Scroll, flip back and forth. H3O plus, HCO3 minus. Okay, so this is my base, and this is my acid. So this means that this is base, this is base, this is acid, this is acid. Okay, so if I were to finish this Bronsted-Lowry, acids donate, so H3O becomes H2O plus, which is your conjugate base. This gains one more, so now instead of just one H, we have two, so H2CO3. Bank account was at -1, you added a positive, so now you're neutral. CAVA equals CBVB. We want to rearrange to solve for VB. These two are being multiplied, so the opposite is dividing. We want to get VB by itself, so we want to move this puppy. Divide by CB. What you do to one side, you do to the other. CB. CB's cancel, and you're left with VB. VB equals bracket CAVA, and if you don't put brackets, you will get the wrong answer. So it's important that you're following along so that you know where all your numbers go, where they came from, and why. So we get 0.200 moles per liter times 75.5 milliliters divide 0.150 moles per liter. Oops. Moles per liters cancels, and you're left with milliliters, which makes sense because you have the volume of your base. Now you calculate. So 0.2, oops, sorry, I forgot brackets again. 0.200 times 75.5, close your brackets, divide 0.15. So I have 100.5 0.1. So if I only want 3 numbers, the 6 tells the 0 to round up to a 1. So we have 101. 101, and again, milliliters. Okay, so now you need to attempt question 3 and 4 by yourself. Why use titrations? The reason why we use them is because they're very quick. It's a relatively inexpensive equipment compared to others. You get consistent results, which makes you more confident in your results. So strong and weak acids. The more hydronium ions you have, the stronger the acid. And that it means the weaker the base. So this is higher on the table of acid and bases. Less hydronium ions means a weaker acid or a stronger base, because remember, acids and bases, due to Bronsted-Lowry, they can be both. Whichever one's higher is acting as the acid. In terms of Bronsted-Lowry acid and bases, explain how carbonate ions neutralize the hydronium ions from the acid. Include a reaction in your answer. So this was talked about in last lesson. So just look back at buffering capacity. That is a very important concept. Okay, make sure you try 3 and 4 to make sure you've done it right, and then attempt the Google form for titrations. Bye guys.